Hello everyone, I welcome you all in this lecture. So in this lecture we will continue from the previous lecture. In previous lecture we have discussed the aircraft model in loop mill simulation. So we will continue. In this lecture we will see when you design the controller how it will look like when you write or when you implement in any other software like a MATLAB and Simulink. Okay, and since a detailed content you can find out using our paper which is published already, where we have discussed in detail about the autopilot design. Okay, so there you can see the detailed mill simulation. Okay, now, so if you want to implement a mill simulation in a MATLAB and Simulink environment or any other software, you have to consider what type of controller you are going to design and for what purpose. So since if you are want to see, it can be you can design the flight control for any kind of fighter aircraft, any kind of unmanned aerial vehicle, small category, medium, okay, and then some multi-rotor or hybrid type of aircraft. So for our case, we have taken simple glider aircraft. Okay, so you need to consider the model. Okay, before designing the control, before doing the mill simulation. Okay, now and decides the envelope. Since we have already covered these things lecture, so I will not go in detail because this flight envelope lecture already we have taken. Already I have taken the separate lecture on this, but just to recall, you have to decide the envelope, and this is a full envelope. This is a inside you have a autopilot envelope. Okay, and you can see there is a 2.12, or you can start from here 1 2 3 4, the 4 corner point, and this is you can see one more point, this is midpoint, and this is one more point. So total 7 point is there. So you can design the controller at the 7 trim point. Okay, not see there is a many uh, trim points here right inside the envelope. So you need to design the controller for all trim point. You can take a 7 trim point if model is not very much highly non-linear. So since glider is not highly non-linear, so 7 trim point is enough. Okay, and then you can schedule the gain for other trim points. Okay, for example, like if you consider the any other aircraft, fighter aircraft, there is a highly non-linear aircraft, so you the trim point is more than lakhs, but here is only 7. Okay, now you can see this is a typical flow chart of a controller design. So you can see up to here this is a model illumination. Okay, so we will do in MATLAB, this we will do in MATLAB, this up to this model illusion. So we can also include this we will do in the MATLAB and Simulink environment. Okay, and then we will convert everything into the compiled code flight software package like. Okay, that becomes the seal. Okay, and then the uh, controller becomes the hardware, and you can actually perform the hardware testing. Okay, so I have some basic microcontroller. This is the Arduino. So actually you can actually do the simple exercise from this microcontroller. For example, simple PID control design, and then simple quad rotor stabilizations you can do. Okay, you can start from the basic one, and then when you enough mature you can go to the PICSOC, and then once you have done everything you can actually design your own board, own PCB, and deploy your our code and fly the aircraft. Okay, so basically now see up to this everything is software only. Here also software but in a compiled package, but here you will see the hill hardware in loop simulation where the controller will be hardware and aircraft will be still in the Simulink. Okay, and once you have done, then you can actually make a small scale model and you can do the flight test. Once the set results are okay, then you can go for a envelope inspection. That means you can actually design the full scale aircraft. So if you have any doubt in this, actually you can ask. Okay, here it is not a real hardware, please note that it is you have model in the assembly. Okay, so I think this everything we have covered already in the lecture, like how will you linearize, how will you do the linear and non-linear analysis. Okay, aircraft model, about everything we have discussed. Okay, flight envelope we have discussed. Okay, controller design we have discussed, model in loop simulation. Okay, so all the control loops we have theory as well as the implementation in separate lecture I have uploaded. The playlist name is system dynamics and control with MATLAB and Simulink, where you can see all the controls loop I have implemented in the MATLAB Simulink. Okay, and the theory part I have covered in the flight control system design course. Okay, all right. So now, so I request you go back to flight control system design course and just see how I have discussed the different flight phases controller. I mean to say different. I have discussed different control loops like roll hold control, heading hold control, speed control loop, altitude hold control loop. Okay, pitch control loop. So all the controls loop we have already discussed. Okay, and we have the same we have implemented in the MATLAB and Simulink also. Let's say you have designed the controller for a takeoff, climb, cruise. Okay, takeoff. Okay, climb, cruise. Okay, loiter, descent, landing. Okay, now this is the radio button I have given. When you press, the controller will be activated. Okay, this is a complete aircraft model that also separate lecture I have taken, and this is the atmospheric disturbance, where we have model where you can see horizontal wind, wind shear, turbulence. Okay, now so I have covered already the aircraft control loop, where I have taken the transfer function. Like for example, I have started with the Q by Delhi transfer function, where you give the delta E input and you will get the Q, and then after once you close this loop, and then next loop becomes the theta loop, and then next loop becomes the altitude loop. Okay, so this is the architecture of complete altitude hold loop. So this is basically the cruise controller. Okay, and in loiter I have already discussed how to hold the bank, how to hold the heading. Let's become the loiter one. Okay, so likewise we have covered all the control loops. If you have any doubts, please ask, I will try to explain. But in that we have considered the transfer function like q by delhi, p by delay, beta by delta r. Okay, but you design the controller, you have to remove the transfer function and put the actual nonlinear model, and then supply the output. So what is the basically what is this output? This is only 4 primary controls, right? This output. This is nothing but the delta E, delta A, delta R, and delta T. After putting everything, actuator dynamics, physical constraints, you will get the this aircraft primary controls. This is going in the aircraft seatbelt simulation. Okay, this block. But what so far in control design we have taken a transfer function like q by delhi, and we have designed the controller PID controller. Let's say we have designed, but in a final mill implementation, you need to replace this transfer function and put the actual nonlinear, because our actual model is nonlinear only. Okay, so here you can see that our aircraft and controller both are sitting in a MATLAB and Simulink environment. So that is called mill. Okay. Now when you convert this code into the complete software package that can be executable and can be deployed into the real hardware, then this becomes the software in loop simulation with all embedded logics, okay, and constraints. Okay, that becomes the SIL. Okay, and then once you deploy the code, everything, for example, like a in this microcontroller or Pixar, I mean to say, or in your own flight controller, then that becomes the hill, because in this case now you will give the command, this command delta a delta a delta delta t from the hardware, but plant will still be sitting in the software. So that is called hill. Okay. Now once you have satisfied, that means your controller is perfectly working, aircraft is behaving well, then you can make a small scale model. In this case, this is, let's say, small scale model, and this is a controller both in a hardware stage. So this is called, you can say, real flight test. And once you satisfied with the scale model flight performance, then you can actually convert this, or you can expand the envelope. I mean, you can go for a bigger size aircraft, which is your actual aircraft. Okay. So if you have any doubt here, you can see. And here one more block, you can see this is gain scheduling. So you can schedule the gain based on speed square, or dynamic pressure half rho v square. Because already you have designed the controller at a 7 trim point, right? So for other trim point, you can schedule the gain based on these three logic: speed square, and dynamic pressure. Why these three? See, for example, let's say if aircraft is not highly non-linear, then single controller gain will work, but different performance at a different trim point. Okay. But if you want to consistent performance, you can actually use a speed or a speed square. Okay. And then when the model is highly non-linear, you should take a dynamic pressure. Okay. Already I explained to you about how will you do the gain scheduling, how will you find the new gain. Okay. That you can go and see the lecture. Okay. Like for example, if you have designed the, if you consider one this trim point, and this is, let's say, one speed, and this is another speed. This you can see, this is v1 and v2, and this is v3, and if you have a gain, this, let's say, k equal to 1, and if you find the new gain, so what you will do, you will find out the dynamic pressure here. Okay. And dynamic pressure here. So what will be the new gain? So new gain at this point will be dynamic pressure of this one half rho v2 square, and then dynamic pressure of this half rho v3 square, and you multiply by this into gain at this point, let's say k. Okay. So when you increase the speed, the gain will drop, because this gain is half rho v square. This value half rho v2 square divided by half rho v3 square will be less than 1. And what we will do in this case, here what we will do, half rho v2 square half rho v1 square multiply by this gain here. This will become the k new for v1 point. Okay. So here this value will be greater than 1. So if at a lower speed, you have to increase the gain. Okay. So already we have discussed in detail. Okay. Not a problem. Okay. All right. So this is the results. So in that paper you will see the detailed result, but here I have put only altitude plots. So you can see the climb phase, take first starting from the takeoff phase 0 to 1, and then climb, and then cruise, and then finally descent, approach, and then finally landing. Okay. So this point you can see, this flight phases you can see. Okay. Now, as I said that in the same mill simulation, you can replace the linear controller by the non-linear controller, and you can actually have a result. So what we have done, we have actually replaced the PID using the INDI controller and sliding mode controller. So this is the results of the sliding mode controller. I mean, so either you can use non-linear dynamic inversion, sliding mode controller, or incremental non-linear dynamic inversion as a non-linear controller, and you can compare. So I am saying that both controller can achieve the same response, but in a linear case you should have a very tight gain scheduling, but in non-linear case you will not have gain scheduling problem. That also we have discussed why. Okay. So I mean to say, if you want to match the performance, absolutely no problem. With a linear and non-linear controller, you can match the performance, absolutely no problem. Okay. All right, so these things you can actually do in the mill. Okay, and once the mill simulation is completed, you can convert this code, because whatever the code you have written in the simulink, that is not you can directly apply. Okay, you have to convert in the standard language here in C++, compile this code, make a software package with embedded constraint logic and all, then this becomes the sim. Okay, and then as I explained to you, then go for a hill, and then finally flight test and spend them. So if you have any doubt, please ask us. I will be happy to answer. We'll meet in the next class. Thank you so much.